Hi, folks. How y'all doing? Um, we're starting section 4.3 today. This is on similarity. I think this is going to be a pretty short video, but let's go ahead and get started. So I want to review with some things that we saw way back on the day 10 video about converting from standard coordinates to alternate coordinates and back and forth. So what we have right now is a basis, an alternate basis that consists of the vectors 1, 1 and negative 1, 1. So 1, 1 is right here, and negative 1, 1 is here. And I want to talk about this vector here. Um, when we see this little b under it, we're saying that this doesn't mean 3 in the x direction and negative 2 in the y direction. It means 3 of this vector and negative 2 of this vector. So that's 3 copies of 1, 1 and negative 2 copies of negative 1, 1. Or if we draw that on here, it's taking this vector 3 times and then following it with this vector negative 2 times. And where do we end up when we finish? So that's in the top row is 3 negative times negative is positive, so 3 plus 2 is 5. In the bottom row, 3 minus 2 is 1. And so in the standard coordinates, this is equal to the vector 5, 1, 5 units to the right, and 1 unit up. Just a reminder is if we want to go from alternate coordinates to standard coordinates, we just take this matrix made out of the vectors of B and we multiply it by the coordinates 3, negative 2. When we multiply, these are weights, and so this is just 3 times 1, 1 plus negative 2 times negative 1, 1, which is exactly what we did right here. So it's a linear combination written as a matrix times a vector. But what if we want to convert in the other direction? We're still looking at the basis 1, 1 and negative 1, negative 1. But now we're looking at the vector negative 1, positive 5. So that's negative 1 in the x direction and 5 units in the y direction. And how would we write that vector as a combination of vectors in B? So this is a slightly harder problem. We know that there is some number of vectors 1, 1 and some other number of vectors negative 1, 1 that when we add them together, we get negative 1, 5. But that's the same thing as saying that x minus y is equal to negative 1 and x plus y is equal to 5, which is solving this system. And when we solve this, we get that x is equal to 3 and y is equal to, no, x is equal to 2 and y is equal to 3. 2 minus 3 is negative 1, 2 plus 3 is 5. And so what that's saying is that if we take 2 copies of this vector and 3 copies of this vector, 1, 2, 3, we end up at negative 1, 5. Um, But this is a row reduction problem. This is taking this matrix here, um, solving times the matrix, the vector xy, which we don't know, and the answer is negative 1, 5. We're going to do one more review example, and then we'll start with the new material. Because we have two ways that we can solve this. The traditional way is to row reduce this system. But the other way is that we can find the inverse of this matrix and multiply the inverse on the other side. So let's try that. Compute the inverse of the matrix, 1, 1, negative 1, 1, 1. So let's do that. A inverse is 1 over the determinant. 1 minus negative 1 is 2. The main diagonal switches places, but they're both 1, so you can't tell. The other diagonal changes sign, so this becomes 1 and this becomes negative 1. And so we get 1 half, 1 half, negative 1 half, positive 1 half. And now we're going to take this matrix and multiply it by negative 1, 5. Well, that's a linear combination. We're going to take negative 1 times 1 half, 1 half, sorry, let me make this bigger, 1 half, negative 1 half, plus 5 times 1 half, 1 half. In the top row, we have negative 1 half plus 5 halves is 2. In the bottom row, we have positive 1 half plus 5 halves, and that's 3. And that's exactly the same matrix, or same vector, that we got in the previous example. X is equal to 2, y is equal to 3. So the process of converting back from standard to alternate can be done in two ways. We're going to solve by row reduction, or we can do it by multiplying the inverse of this matrix by negative 1, 5. And with that, we're ready to go ahead and start with the new stuff. That's going to use some of this review material in the next section. Are we ready to get started? Let's go. So let's look at this matrix here, 1, 1, 2, 2. This matrix has eigenvectors 1, 1, and negative 1, 1, and the eigenvalues are 3 and 1. We've done this before, but let me just review how did we find this information. We find the eigenvalues first by subtracting lambda from the diagonal. 1 minus lambda, 2, 2 and 1 minus lambda. We'll take the determinant of that and set it equal to 0. And so that's 1 minus lambda times 1 minus lambda minus 4 is equal to 0. When I multiply this out, I get 1. The middle terms are minus lambda and minus lambda, so that's minus 2 lambda. And the last terms are plus lambda squared minus 4 equals 0. I can rearrange that to lambda squared minus 2 lambda. 1 and negative 4 is negative 3. And this factors into 1 lambda minus 3 and lambda plus 1. And so we get lambda is equal to 3 and lambda is equal to negative 1. That's how we get the eigenvalues. To get the eigenvectors, we're going to plug in 3 and -1 in for lambda here and row reduce the two homogeneous systems. So the homogeneous with lambda equals 3 is 1 minus 3 is -2. And again, 1 minus 3 is -2. And the homogeneous system with lambda equals to -1 is 1 minus -1 is +2. And again, 1 minus -1 is +2. Both of these matrices are easy to row reduce. This one will take row 2 plus row 1. And that gives me -2, 2, 0, and 0, 0, 0. And so negative 2x plus 2y is equal to 0, or negative x plus y is equal to 0. That's just saying that x and y are the same, and that gives us the vector 1, 1. X could be 1 and y could be 1. The other matrix we row reduce by taking row 2 minus row 1. And this says that 2x plus 2y is equal to 0, or x plus y is equal to 0. And now x and y have to be opposite signs, and that's where we get x is equal to -1 and y is equal to +1. We could have also done this the other way around and said x equals 1, y equals -1. And that would have been okay also. But that's how we get these two eigenvectors. Okay, so we now know what the eigenvectors are, and we know what the eigenvalues are. So we know from last time that the linear transformation that we get by taking a times x takes this alternate basis made out of these two vectors, and it scales the vectors, but it doesn't rotate them. This vector gets scaled by a factor of 3, and this vector gets scaled by a factor of -1. So my question for you, and I hope you can figure this out, is what matrix has the same effect on the standard basis? In other words, what matrix will scale E1 by 3, and this should be an E2, sorry, E2 by -1 without rotating them? What matrix does this on the standard basis? Well, we know that on the standard basis, the columns of the matrix are the transformed versions of E1 and E2. So if the E1 gets scaled by 3, then this transformed version of E1 is 3, 0. If E2 scales by -1, the transformed version of E2 is 0, -1. And so that's the matrix 3, 0, 0, -1. In other words, this matrix does on the standard basis what the starting matrix we had does on this alternate basis. So let's start with some definitions here. A square matrix D is called a diagonal matrix if its only non-zero entries are along the diagonal. In other words, in positions 1, 1, or 2, 2, or 3, 3, or so on and so forth. So this matrix here is a diagonal matrix. And our other definition, let's say we have two matrices. We say that they are similar matrices. This is a term we're defining. If there's a basis that works for A1 and a basis that works for A2, so that the transformation A1 scales B1 by some amount, and A2 scales B2 by the exact same amounts. In other words, this matrix here is similar to this matrix because this matrix scales the alternate basis by 3 and -1, and this matrix scales the standard basis by 3 and -1. And so we have found an example of similar matrices. So let's follow up on what we just saw. By this example, we know that these two matrices are similar because A scales this basis by the exact amounts, 3 and -1, that this matrix scales the standard basis. So A and D are doing the same geometric thing, but they're doing it to two different bases. But by the example we did at the beginning today, the review example, we know that we can convert vectors between bases using the matrix formed from the vectors of B. So if we start with a vector in B coordinates, we actually have two choices. We can just scale them using the matrix A. So I have a vector in B coordinates, and since they're already in B coordinates, I can just use the matrix A times that vector, and it will scale the first vector by 3 and the second vector by -1. Or we can take this vector and convert them into standard coordinates by multiplying by the inverse of P1. P1 times these alternate coordinates will give me a vector that's in standard coordinates. And now that they're in standard coordinates, the matrix D does geometrically exactly the same thing, but now it's doing it in standard coordinates. And then, now that we have done the geometric transformation in standard coordinates, we can convert everything back using the matrix P. P inverse goes from alternate to standard, then P goes back from standard to alternate. And this combination should do exactly the same thing that A does. In other words, A and this combination give me the same answer. And we call this the similarity formula. This should be an equal sign and not a minus sign. The n by n matrices A and B are similar if and only if there's a change of coordinates matrix such that A is equal to this combination. This matrix converts into standard coordinates. This matrix then does the geometric transformation into standard coordinates, and then this matrix changes everything back. This is similar in concept to U substitution. We make a substitution of function from x's to u's. Then we can integrate in x in terms of u. Then we can convert back in terms of x. Um, Conceptually, that's the same kind of thing we're doing here. We are using a change of coordinates matrix to make a linear transformation potentially easier. In the next lesson, we're going to see some examples of this and some problems for which this is useful. But like I said, this is going to be a short video, and we are done. Thank you for waiting.